Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about overfitting in linear regression. We're going to use real data and theoretical analysis to study the training error of linear regression models in order to understand when we can expect these models to overfit or not overfit. Let's get to it. We're going to study the training error of linear regression models. Regression is the problem of estimating a quantity of interest, which we call the response, from multiple other quantities, which we call features. We're going to be using an example where we estimate the temperature at a certain location, in particular Versailles, Kentucky, from temperatures at multiple other locations, specifically 133 other locations all over the United States, so that we will have 133 features. When we model the response as a random variable y and the features as a random vector x, where each entry corresponds to a feature, then the optimal linear estimator of the response given the features has this form. We center, and we derived this in our video on linear minimum mean squared error estimation. What we do is we first center the features removing their mean, then we take an inner product with a vector of coefficients that depends on the covariance matrix of the features and the cross covariance between the features and the response. And finally, we add the mean of the response. In general, in our analysis, we're going to assume that both the features and the response are centered, so that we don't have to worry about these additive constants. The key question that we want to study in this video is how well do linear models fit the data? And do they fit the data too well in certain cases? And you'll see very soon what I mean by that. In order to start studying this question, let's assume that the response is indeed a random variable and the features are indeed a random vector, and that the response is given by a linear function of the features governed by these true coefficients, which are just a fixed vector of coefficients, plus a noise term that is independent from the features and that has variance sigma squared. For simplicity, we're going to assume that everything is centered so that we don't have to worry about additive constants. Now let me ask you a question. Under this assumption, what do you think the mean squared error of our linear model should be ideally? In particular, do we want it to be as small as possible? So I would recommend that you pause the video for a moment and think about it. The answer is no, we do not want it to be as small as possible. If we have a linear model that is estimating the data too well, this might mean that we're overfitting the noise. We're going to make that much more precise in a moment. Said otherwise, here the only thing we can hope to estimate from the response as a function of the features is this component. We cannot possibly estimate this component because it is independent from the features and our linear model only sees the features. Therefore, the mean squared error here should equal to the mean square of that component because everything is centered to have zero mean. That's the variance of the noise. So we should observe a mean squared error of sigma squared. In a previous video on coefficient error, we derived the coefficient estimates provided by the linear minimum mean squared error estimator in this case, when we assume that the response is indeed a linear function of the features plus some additive noise. We proved that under our assumptions, the coefficients actually recover the true coefficients, which is great because then when we look at the error of the estimator, we're going to plug in here our assumption about the response. We're going to plug here the fact that we recover the true coefficients. What we see is that the estimate of the response provided by the linear model does correspond to the linear component and has nothing to do with the noise component. These two guys are going to cancel out so that we're not estimating the noise, and our error indeed corresponds to the mean square of the noise and is equal to sigma squared. So linear estimation under these assumptions works. Is this the end of the story? Can I stop the video here? Absolutely not, because when we fit linear models, we fit them to data. We do not have access to the true distributions, whatever that might mean in practice, of the feature and the response. We do not have access to the true cross covariance or between the features and the response, or the true covariance matrix of the features. We have to compute all of this from data. So up to now we have been talking about this random variable y and this random vector x, but in practice what we have are examples. So these are n examples. Each of the examples corresponds to a feature vector and the corresponding response, and we have n of those. N is our number of training data. This is called a training set because it's what we use to train the linear model. And what we do in order to train a linear model on this kind of data, as we explained in the video on ordinary least squares, is basically construct the ordinary least squares estimator, which is very similar to the linear MMSE estimator, except that instead of the cross covariance between the features and the response, we're using the sample cross covariance between the features and the response observed in the data. Same thing for the sample covariance matrix of the features, which replaces the true covariance that we assumed was available when we were just having our probabilistic estimation. And we also use the sample means of the features and of the response. So now we're going to study the behavior of the training error for the ordinary least squares estimator. In order to do that, we're going to look at a real data set which contains temperatures from 2015. Our goal is to estimate the response at Versailles, Kentucky, using 133 features, which are temperatures at other locations in the United States. We already talked about this example in our video on coefficient error. Here I'm plotting the location corresponding to our response, which is that star, and I'm also plotting these circular markers whose radius is proportional to the size of the coefficients in our linear model, in our ordinary least squares model, when the number of data is large. I've highlighted those three coefficients because they dominate the others and they make a lot of sense. Essentially, we're estimating the temperature at Versailles, doing a weighted average of locations that are nearby, and we're ignoring the other locations. This is a graph of how the coefficients evolve for different amounts of training data. When we have a lot of training data, we see that these three coefficients that are bolded, which correspond to these very reasonable locations, dominate, and the rest are very small. But when we don't have a lot of data, boom, the coefficients go bananas, essentially. That's a summary of the video on coefficient error, where we analyzed this phenomenon very carefully. In one of the examples in the coefficient error video, an example that was very simple with just 4 data points, we saw that noise amplification in linear regression coefficients has a simple explanation in the sense that it allows you to fit the data better. So let's see whether this is the case on a real data set by plotting the training error for these different numbers of training data. This is the training error for all of these models corresponding to a coefficient that you just saw. The training error is just the sum of squared errors on the data that we have used to train the model. I'm also showing you the similar errors on a training set that is held out, and we call that the test error. You can see this. These are the black markers. So what do we observe? When we have, and I'm going to erase all of these arrows so that I can show you more clearly. When we have a lot of data, we observe that the linear model incurs essentially the same error in the test set and in the training set, indicating that the linear structure that it has uncovered actually generalizes, so it's truly associated with the response. This corresponds to the regime where it seems like the linear coefficients are actually very reasonable. However, when we have less data, what do we observe? We observe that the training error becomes smaller and smaller and smaller. So you might naively think that maybe your linear model is becoming better and better, but that's not what's happening, because when you look at its performance on held out data, it's really terrible. So this is the situation where the coefficients are going bananas, and they're going bananas because they're fitting structure in the data which is not really truly linearly associated with the response. We can see that because that doesn't generalize. So we're seeing overfitting. And in this video, we're going to try to understand why overfitting occurs in linear regression models and under what circumstances. In order to do that, we have to abandon our model where our response was additive in terms of the, linear in terms of the features, and the features were a random vector. Now what we're going to do is we're going to still study a case where the response is linear with respect to the features, but we're going to fix those features so that we have a finite number of data. So just to be very clear, we're going to look at a situation where we have n examples. Each of the examples corresponds to a vector of d features. So these are the d features for the first example, d features for the second example, down to the nth example. Each of those feature vectors, so how do we obtain the response corresponding to each example? Well, we take the inner product with these fixed true coefficients, okay, because our assumption is that the response is linearly related to the features. So each of these guys is going to, we're going to take the inner product with each of the coefficients, and then we're going to add additive noise, okay, a sample of additive noise, not a sample, like an additive noise variable to each of the measurements. And this is going to give us the training response. Okay, you're going to forgive me for not writing subtrain to not make things cluttered, but hopefully this makes sense. This is a modified model that is going to help us understand what happens when we have finite data. Okay, but still we keep this assumption where the response is linear with respect to the features, and there's this additive noise term that has nothing to do with the features. We're going to assume that the noise is IID and has variance sigma squared. Perfect. So for simplicity, everything is going to be centered so that we don't have to care about additive constants. Now let's take a linear algebra perspective on our linear model. So when we're fitting the training data, what are we doing? We're taking the inner product of the d features for the first example with our estimated coefficient, and that should approximate the first entry of the response. Then we take the inner product of our second set of d features with the same coefficients, and that should approximate the second entry of the response, and so on and so forth. Okay, where we're basically trying to approximate the n examples of the response using inner products of the corresponding features with the coefficients. And then we need to find the value of the linear coefficients such that this approximation is as good as possible. That's what we do when we do ordinary least squares estimation. We can write this in terms of this column. So this first column corresponding to the first feature in the n examples, that's the first column of this matrix that is hitting the coefficients in order to estimate y train. Okay. We call this matrix the design matrix. I'm going to be referring to it as the design matrix going on. Basically, this is the matrix that we obtain when you put all of these feature vectors together. When they hit the coefficient vector, we want it to approximate the response vector as well as possible. And we're going to have this notation where x1 is the column corresponding to the first feature, x2 the column corresponding to the second feature, xd the column corresponding to the last feature. Great. If you know your linear algebra, you will know that when we have a matrix that hits a vector, the product between the matrix and the vector is equal to a sum of the columns weighted by the corresponding entry of the vector. So here, what we're doing is we're taking this column, which is an n-dimensional vector, scaling it using this coefficient, and then summing it to a scaled version of the second column, and then summing it to a scaled version of the remaining columns. So just to summarize, we're using the n-dimensional vectors we're scaling them by the corresponding coefficients. Okay, we're doing a linear combination of these d n-dimensional vectors to hopefully approximate this vector, which is y train, okay, which is also n-dimensional. So we're using this n-d-dimensional. No, I said that the other way. By the way, I recorded this video up until this moment, and I basically wrote n-d-dimensional vectors as opposed to d n-dimensional vectors, so I had to re-record it completely, and now I almost made the same mistake. So I want to be very clear, okay? N, which is the number of training data, that's the dimensionality of these vectors, and the number of vectors that we have is d. Now let's draw a picture to hopefully make this clearer. So imagine that we have d is equal to 2. So we only have 2 feature vectors, and n is equal to 3, so that they're 3-dimensional and we can look at them. Now, any possible linear combination of two vectors spans a plane. Okay, in this case, the plane is in this 3-dimensional space because n is equal to 3. These 2 vectors represent x1 and x2, the first and the second column in the design matrix. When we are fitting an ordinary least squares model, what we want is to approximate the response vector, the n examples of the response, in this case 3, as closely as possible using linear combinations of the columns, and as I just showed you. And geometrically, what does this mean? We need the point on this plane that is as close as possible to this response vector in terms of the sum of squared entries, which is the L2 norm. So you remember your algebra, what is that point? It's just the projection of the response vector onto the plane spanned by the columns of the design matrix. And that's exactly equal to the response estimate provided by the OLS estimate. We're not going to prove mathematically that this is the case, but it's not so difficult to prove. Essentially, what you do is you write the OLS coefficients in terms of the design matrix, and then you apply the singular value decomposition. That's in the book. You can take a look at the proof there. But for now, for this video, maybe just believe me that you can actually, that the estimate provided by ordinary least squares for the response is exactly equal to the projection of the observed response onto the column space of the design matrix. Why? Again, because we're using a linear combination of those columns to approximate the response vector as well as possible. So in that case, now if we're assuming that the response is equal to this linear function of the columns of the design matrix plus some additive noise, if that is the case, then when we look at the error incurred by ordinary least squares, so the observed response minus the estimate provided by ordinary least squares, under this assumption where the response indeed is a linear combination of the features but it's corrupted by noise, then the error is going to be the observed response minus the projection of the observed response onto the column space. Okay, we proved this through this geometric argument. That is going to correspond to the projection of the response vector onto the orthogonal complement of that plane. So just to show you what this means. The orthogonal complement would be, in this case, a line like that, which is orthogonal to that plane. And what this is saying is that if you look at the error, well, this vector, because this is an orthogonal projection, has to be basically, the error is going to be in here. Okay, so it corresponds to the projection of the response onto the orthogonal complement to the plane. In this case, this orthogonal complement has dimension 1 because n is 3 and the plane has dimension 2 because there are only 2 features. Okay, so hopefully it makes sense that the error of, or the response estimation error of ordinary least squares is the projection of the observed response onto the orthogonal complement of the column space of the design matrix. Now, under our assumptions, the response is equal to this linear combination of the features plus this additive noise. A projection of the sum of two vectors is just equal to the sum of the projections. What is this projection equal to? Well, if you look at the projection of the linear component lives completely within this plane. Okay, the linear component is somewhere here. Because it's a linear combination, we're assuming that it's actually a linear combination of the features. So it's completely orthogonal to that orthogonal complement. So that is going to be 0. Okay, hopefully it makes sense that this guy is just going to be 0 because of that. And we're left with the projection of the noise onto the orthogonal complement of the column space of the design matrix. So basically, how much noise, what is the noise component that is preserved after we do that projection? And if the noise is equally distributed in every direction, which if this is random noise you would expect, you would call this isotropic. If you have IID, for example, Gaussian noise, you would see that, like the same variance in every direction. Then my question would be how much, what would be the variance of this guy in that case? I think the way I phrased that was a little bit strange, so let me try again. Okay, so we have shown that the error is equal to the projection of this noise onto this noise vector onto the orthogonal complement of the column space of the design matrix. Okay, so now if it has the same variance in every direction of space, this is an n-dimensional vector, the amount of variance captured by that projection should be proportional to the dimension of the space of the subspace that you're projecting on. Okay, so hopefully that was a little bit clearer. In the case of our example, this was just one line, so you would expect just it to be proportional to 1, right? If you were projecting onto a plane, you would expect it to be proportional to 2, and so on and so forth. 2 times whatever variance it has in every direction. If it has sigma squared in every direction, then it would be 1 times sigma squared if you're projecting onto a line, 2 times sigma squared if you're projecting onto a plane. So in general, when we have d feature vectors that are n-dimensional, the subspace spanned by the columns is d-dimensional because you only have d columns. So what is the dimension of the orthogonal complement? By basic linear algebra, it has to be n minus d. So we're projecting the noise onto a subspace of dimension n minus d. This means that the training error is going to be proportional to n minus d. We're going to it's because it's the variance captured by the projection. We're assuming that this noise vector is completely independent from everything, so it has the same variance in every direction. So we would expect the training error of the ordinary least squares estimator to scale as sigma squared times n minus d for this reason. Okay, so notice what happens when n is very large. When n is very large, essentially we're preserving all of the noise. We're not estimating, if you want, like all of the noise goes into the error, which is good news. So the average training error that we have derived theoretically for ordinary least squares with our linear algebraic reasoning is n minus d times sigma squared, and now we're dividing by n because we have n data points. So the average training error in the training set would look like this. It would be proportional to the variance of the noise, which makes a lot of sense, and then times a factor that is 1 minus d over n. Remember that this is the number of features and n is the number of data points. So what happens when the number of data points is much larger than the number of features? As I said a moment ago in our geometric argument, essentially all of the noise goes into the error, then the average error is equal to sigma squared. So this is actually the situation that we saw at the beginning. In this regime, the linear model does not overfit the noise. The error all goes into the noise. We don't observe overfitting. We have many more data points than the number of features. But what happens when the number of features is similar to the number of data points? Then this is close to 1 and the error is very small. It's close to 0. In this case, there's enough degrees of freedom within the linear model to approximate the noise. Okay, in this orthogonal projection of the noise, most of the noise is actually remains on the plane where our estimate is, okay, in our geometric argument, so that we observe overfitting. And this is, and now we're going to see how well our formula explains what we observe on the real data. So we're going to assume that this is sigma, because in that regime with a lot of data, that is basically the square root of the squared error that we observe, and it corresponds to the test error. If that is the case, now we're going to multiply sigma by 1 minus the number of features, which is 133, divided by the number of data points for the different number of data points, and see whether we can explain the training error that we observed in the real data. And it explains it perfectly. So this geometric argument that I just showed you completely explains the training error that we observe empirically in our real data experiments. So what have we learned? We have learned that the training error of linear models depends on the number of training data n. When n is very large with respect to the number of features, the models are not going to be able to overfit the noise, and we're not going to observe overfitting. But when n is similar to the number of features, then the linear model is going to have the flexibility to fit noise that is unrelated to the features, and we're going to have overfitting and poor generalization to held out data. And that's all I have. Thank you very much.